Galileo asked us to imagine a sealed cabin below deck on a smoothly moving ship. The flies fly normally. Water falls into a cup. A tossed ball lands where it should. Without a window, no experiment inside tells you whether the ship is docked or gliding at constant speed. That is the original principle of relativity. Smooth motion has no special badge saying, "You are the one who is moving." On a modern train, toss a ball straight up. To you, it rises and returns along one vertical line. A person on the platform describes the very same toss differently. The train carries you and the ball forward, so the ball traces a long arc across the platform view. Both pictures are right. A path through space depends on who draws the coordinates, but the ball still lands in your hand. Everyone agrees about that meeting. Relativity does not mean that anything goes. Descriptions change. Physical events do not. For ordinary balls, the longer path comes with extra sideways speed, so both observers can still share the same seconds. Light is where that comfortable arrangement breaks. In everyday life, speeds add. Throw a ball forward from a moving train and the platform measures the throw plus the train. The rule is so familiar that it feels like common sense. Light refuses the rule. Chase a beam, flee from it, or watch its source pass by. Every inertial observer measures the same speed of light in vacuum. More than a century of experiments agrees. So three comfortable ideas collide. The laws of physics should be the same for every smoothly moving observer. Light should have the same measured speed for each of them, and everyone should share one rigid space and one universal time. All three cannot survive. Einstein keeps the first two. Space and time are the things that give. A light clock makes the consequence visible. One pulse bounces between two mirrors, and each round trip is a tick. Ride beside the clock and the pulse travels straight upward. Watch the clock move past and the top mirror slides sideways while the pulse is in flight. The pulse must cross a diagonal to meet it. The tick still happens. A change of viewpoint cannot turn a hit into a miss. Now compare the two pictures. The diagonal path is longer. Light has exactly the same speed in both pictures. A longer trip at the same speed must take more time. That is the whole heart of time dilation. The moving clock takes longer to tick in the platform description. This is the inversion. The beam, which seems as though it ought to change speed, holds steady. Space and time, which seem rigid, adjust around it. The triangle can tell us exactly how much, but the big idea is already on screen. Perhaps the light clock is merely peculiar. Put it beside an atomic clock, a spring, or a heartbeat. If they drifted apart just because the cabin moved smoothly, that disagreement would reveal the cabin's speed. Galileo's sealed room principle forbids that. Every physical process must share the same elapsed time. This is not a story about broken clocks. It is a statement about time. Nature lets us check. Unstable particles called muons are born high in the atmosphere and race toward the ground. At rest they vanish too quickly to make the trip. Yet fast muons arrive in abundance. Their short internal lifetimes stretch across much more of our time, just as the light clock predicts. Atomic clocks on planes and satellites tell the same story with exquisite precision. A clock measures the time along its own route through spacetime. In the next episodes, those routes become worldlines, and the amount of time inside a path will become part of the geometry itself. Imagine lightning striking the front and rear of a long train just as it passes a station. A platform observer stands exactly halfway between the two places where lightning hits. The flashes race inward at the same speed. Because the paths are equal, they reach the platform observer together. The platform observer's verdict is clear. The two distant strikes happened at the same time. They were simultaneous in the platform frame. Now follow a passenger at the midpoint of the moving train. In the platform description, the passenger travels toward the flash from the front and away from the flash from the rear. The front flash reaches the passenger first. The rear flash catches up later, but unequal arrival times are not yet the passenger's conclusion. In the train frame, the passenger is at rest halfway between the two ends, and light travels at the same speed in both directions. Under those conditions, the front flash could arrive first only if the front strike happened first. The rear strike happened later. The platform says simultaneous. The passenger says front first. Each verdict belongs to its own frame. A spacetime diagram turns that story into geometry. Up the page is time, across the page is space. The observers can agree on the event where they pass one another. The platform observer draws a horizontal line through events happening now. The moving observer draws a tilted line. Near their meeting, the difference is invisible. Far away, the two lines include different events. Motion does not merely change the rate of clocks. It changes how an observer divides distant events into past, present, and future. There is no single cosmic sheet labeled now that every observer must share. Different states of smooth motion cut spacetime into different presents. This does not make nearby experience unreliable. Everyone agrees when two things meet, when a flash reaches an eye, and when a clock beside you ticks. The disagreement appears when we extend one observer's present across distance. Local meetings are physical facts. Distant simultaneity depends on motion. That distinction will matter when we ask whether a distant event can affect us at all. Set off one flash in empty space. A moment later, its light forms a small sphere. Later still, a larger sphere. The surface races outward at the speed of light. Stack those expanding spheres through time, and their history forms a cone. On a flat diagram with only one direction of space. The cone appears as two bright diagonal lines. The event that made the flash sits at the tip. This simple shape is a map of possible influence. Choose an event inside the cone. A slower-than-light traveler or signal can get there from the flash. Choose one exactly on the edge. Only light or something equally fast can connect the two. Choose an event outside. It is too far away and too soon. Reaching it would require an influence faster than light. The cone therefore separates what the flash can affect from what it cannot. A light cone is not merely the route photons happen to take. It is the boundary of causality. Different observers draw different grids across the same spacetime. Their space and time axes tilt, just as their lines of distant now did. But every one of them measures the same light speed, so every one of them preserves the same cone. They may assign different distances and times to an event, but they agree about whether a signal can connect it to the flash. The speed of light is also the speed limit of cause and effect. In relativity, causality has a shape. Two travelers begin together with matching clocks. One remains at home, the other races toward a distant turnaround point. At high speed, the traveler's clock accumulates less time between the same broad stages of the trip. The traveler turns around and comes home. That matters because it brings both clocks back to one place. The comparison is immediate. At the reunion, the clocks disagree. The traveler has aged less. Neither clock is defective. Each has measured the time along a different route through spacetime. Draw the trip on a spacetime diagram. The departure and reunion are shared events. The person at home traces one straight world line. The traveler traces an outward segment and a returning segment. A clock carried along each route places its own ticks on that line. The home route contains more ticks between the same two meetings. The time recorded by a clock along its own path is called proper time. It is as personal to the path as the mileage on a particular road. Yet everyone can agree on it when the clocks reunite. There are many possible routes between the departure and reunion. One traveler could turn gently, another sharply, while the person at home follows the straight route. In flat spacetime, that straight route gives a clock the most proper time between two fixed meetings. This is the reverse of an ordinary ruler, where a straight line is shortest. Spacetime has a different geometry. The animation is the idea we need, proving the general result belongs on paper, not in this introduction. When gravity enters, free motion is still the straightest motion available. But spacetime itself can be curved, so its straightest paths can converge, bend around stars, or fall toward a planet. That is where we go next. Stand in a closed elevator on Earth and release an apple. It approaches the floor, and your feet feel the floor pushing upward on you. Now place the same elevator far from every planet and accelerate it upward. The floor rises to meet the floating apple, and your feet feel the same push. Inside a sufficiently small room, ordinary experiments cannot distinguish standing in gravity from accelerating through empty space. This is the equivalence principle. Reverse the comparison. Let the elevator fall freely beside the apple, and let another cabin drift quietly through empty space. The first cabin crosses the page dramatically, the second barely does anything. Yet inside both cabins, the apple floats beside you. Einstein's happiest thought was that free fall is not the feeling of gravity pulling. Free fall is the natural, weightless motion. The force you feel while standing on Earth is the ground preventing that motion. How can natural paths fall together? Picture two airplanes leaving the equator from different cities, each flying due north without steering sideways. Their routes begin parallel, then meet at the pole. Nothing pushed one airplane toward the other. The curved surface changed what straightest possible paths do. Nearby falling objects behave in a similar way. Their paths lean toward the center of Earth and slowly converge. A perfectly uniform accelerating rocket can imitate gravity in a tiny room. But over a larger region, this convergence gives the game away. That leftover is curvature. Gravity is not an invisible hand tugging every object off a natural route. Gravity is the shape of the routes that freely falling objects naturally follow. The elevator also reveals something stranger. Send regular light pulses from the floor of an accelerating rocket toward the ceiling. While each pulse climbs, the ceiling gains speed and moves away. The pulses arrive spread farther apart than they were sent. The ceiling reads that as a slower rhythm below. If acceleration and gravity match locally, the same conclusion must hold in a gravitational field. A clock lower down ticks a little more slowly than a clock higher up. The difference is tiny across a room, but modern clocks can measure it across less than a meter. And satellite navigation must account for it. Gravity shapes not only falling paths, but the rhythm of time itself. In John Wheeler's memorable summary, matter tells spacetime how to curve, and curved spacetime tells matter how to move. We do not need the field equations to carry that picture forward. Keep a star's mass and squeeze it into a smaller space. Its gravity grows stronger near the surface, clocks there run slower, and escaping light is stretched more severely. Eventually, the star fits inside an event horizon. On a spacetime diagram, the outward edge of the local light cone stands upright. Outward light can no longer increase its distance from the center. Deeper inside, the whole future cone tips inward. Both possible directions for a future moving beam lead towards smaller radii. The beam still moves locally at the ordinary speed of light. What changed is which direction spacetime permits the future to take. An event horizon is not a material shell. A freely falling traveler can cross it without hitting a wall, and near a sufficiently large black hole, the immediate tidal effects at the crossing can be gentle. A local clock keeps ticking. A nearby flashlight still works. The drama is global, not necessarily local. After the crossing, every future-directed route remains inside. Turning around is no longer a route toward the exterior, just as moving toward yesterday is not an available direction here. The horizon is a boundary in causal possibility. Horizons do not belong only to black holes. The space between distant galaxies is expanding. A light pulse always passes its local neighbors at the speed of light, yet the intervening space can keep stretching while the pulse travels. From sufficiently distant regions, light emitted now will never reach us. Those galaxies need not vanish from existence, and nothing locally outruns a beam. The global geometry has simply placed their later events beyond our causal reach. A finite life also has a horizon of a quieter kind. Draw the events that can send a signal into that life, and the events a signal from that life can reach. The overlap forms a causal diamond. Inside it are all the meetings, messages, sights, and consequences that can physically join this history. Beyond it lies most of the universe. The cosmos may be unimaginably large, but every finite observer occupies a limited region of possible contact. Later, that limit will matter more than any formula about it. Watch a simple orbit. Play it forward or backward, and both versions look physically ordinary. Many of the microscopic laws we use have this symmetry. Reverse every motion carefully, and the reversed history is also allowed. An egg falling and breaking feels different. Run that film backward and fragments leap together, seal themselves, and rise into a hand. The laws do not simply stamp "forbidden" on that reverse story. It is fantastically special, because every hidden motion would have to cooperate exactly. So why are ordinary histories full of breaking eggs and never self-assembling ones? Begin with every piece arranged in one neat corner. That picture depends on a very special placement. Let the pieces move and they soon look scattered. There are countless scattered arrangements that all look like the same ordinary mess from a distance, but very few that look carefully ordered. Entropy is the name physicists give to this hidden counting. Higher entropy means more microscopic arrangements fit the same large-scale description. We do not need the formula here. The essential imbalance is visual. There are vastly more ways for an egg to be broken than whole, and more ways for warm coffee to be evenly cool than to gather its heat back into one cup. Fresh snow begins smooth and ready to be changed. A boot presses down, pushes crystals aside, and lifts away. The footprint remains because the snow now occupies one of many disturbed arrangements. Its shape carries information about an earlier event. A clean patch beside it does not carry an equally detailed record of a future boot. Photographs, fossils, scars, and memories are more elaborate footprints. They are present physical structures correlated with earlier, lower entropy conditions. That is why records point backward. The deepest part of the answer lies not in a special future-pointing force, but in the condition from which our universe began. The early universe was extraordinarily low in entropy, unusually ordered in the relevant gravitational sense. From that special boundary, overwhelmingly many ordinary developments lead toward higher entropy. Along those histories, footprints and memories accumulate on one side of events, so creatures inside them remember what they call the past and anticipate what they call the future. A four-dimensional history can sit complete on the page, while every conscious slice inside it experiences a powerful direction. The completed history does not flow. But records within that history give experience a direction. Return to two observers passing one another. They agree completely about their meeting. The station observer extends a horizontal present across distant space. The traveler extends a tilted present. And that tilted line includes a distant event the station observer places later. Neither observer has made a bad measurement. Their different presents are built into relativity. Now comes a philosophical question, not a new experiment. If the distant event is present for one observer and future for another, can we say it is real for one but not yet real for the other? There are several ways to answer. We could let reality itself depend on the observer, so different motions come with different sets of real distant events. That is hard to interpret. We could suppose that one hidden present is the true one, even though relativity gives us no ordinary experiment that reveals it. That adds extra structure. Or we can treat every event in spacetime as real at its coordinates, past, present, and future together forming one four-dimensional block. Then different presents are simply different slices through the same structure. Relativity makes this third picture especially natural. It does not stamp the word "proved" on a metaphysical interpretation. The block picture represents a life, the way a map represents an entire route. Birth, breakfast next Thursday, and death occupy different coordinates along one world line. No luminous spotlight has to sweep over the map and manufacture each event as it passes. That does not mean a person experiences every moment at once. Each event on the line contains only its local experience. Memories and expectations. Change is the difference between one part of the history and another, not an illusion. For the rest of this series, we will use the block universe as a lens because it makes the book's questions vivid. We will keep remembering where the physics ends and the interpretation begins. Imagine approaching a fork in the road. From where you stand, both branches matter. You picture each one, remember what you promised, hesitate, and decide. Viewed afterward, the journey is one completed curve. In a block universe picture, that whole curve is already represented. The branch you did not take is not another event hidden somewhere on your actual worldline. Does that make the decision unreal, or does it simply describe the decision from outside its moment? Zoom into the turn and the curve is not empty. It contains a brain noticing reasons, feeling fear, recalling a promise, imagining consequences, and responding. Those processes are physical events, but calling them physical does not make them absent. They are how this part of the worldline acquires its shape. A compatibilist calls an action free when it flows through the person's own ability to understand and answer reasons, rather than through a gun at the door or a seizure. On that view, a complete worldline contains deliberation. It does not replace it. A map can display an entire road while a traveler still encounters every bend locally. The finished ink does not push the traveler around the curve. It represents the journey, including the places where reasons and actions occur. We should also keep two ideas separate. A block universe says that events at different times are all part of reality. Determinism says that the laws in one state uniquely fix other states. One idea does not automatically prove the other. Most importantly, physics does not decide what the word freedom must mean. It can sharpen the question. The answer still depends on whether we demand an uncaused choice, alternate possible histories, or the ordinary human power to notice reasons and act through them. We have drawn people as thin world lines because thin lines make clean diagrams. A real person is not thin. At every time there is a body, a brain, moving air, exchanged food, and an uncertain boundary with the surrounding world. Carry that extended pattern through time and the line becomes a ribbon. Or a four-dimensional worm. Each cross-section is one momentary person. The whole ribbon is the life. It begins at a birth boundary and ends at a death boundary. The geometry does not hide that finitude. It draws it plainly. Slice the ribbon at different times and we get a child, a young adult, a later body, an older face. The block picture resembles a series of photographs more than one little self traveling between them. Later photographs contain physical records of earlier ones, memories, habits, scars, names, and stories. Those records are partial and reconstructed, but they make each present slice feel continuous with a past. The book puts it this way: you are not a river. You are a series of photographs, each containing the image of a river. The experience of continuity is real inside the photographs, even if the whole ribbon does not flow. A ruler has a final mark. A road can have a final stretch. We do not imagine that the ruler experiences an endless blank beyond its end, or that the road continues as a road made of nothing. In the same geometric sense, death is the boundary of a worldline. Not a later episode in which the person inspects their own absence. This analogy does not make death harmless, and geometry does not cancel grief. It only removes one misleading picture, an eternal state of being dead that someone must endure after the life has ended. In the block interpretation, earlier moments do not fade into featureless nothing. A first day, a handheld, a mistake, and a quiet morning remain the events they are at their coordinates. A later slice cannot travel back to them. It carries only imperfect traces, softened by time and rebuilt by memory. That is the hard combination. The moment is real in the structure, and the separation is real too. Some people find permanence comforting. Others find it horrifying, because pain is also part of the block and nothing receives a second draft. The equations do not tell us which response to have. They give us a finite shape and leave us to live with it. Begin with something ordinary: two people at a kitchen table, two cups, a familiar look across the room. Years later, one person may carry a softened reconstruction of that scene. The memory is here, encoded in a later brain. In the block picture, the original event remains at its own coordinates, with all the detail it had. That sounds like preservation, but it is not access. A later worldline cannot step backward into the kitchen. It carries a changing copy of an event it can no longer touch. Love is not only two lines passing nearby. Words cross the space between them. Light from one face reaches another pair of eyes. Hands touch. Meals are made. One nervous system changes because of what the other did. Every exchange is ordinary causality, traveling inside light cones. Repeated across years, those influences lace the worldlines together. The braid is not a metaphor floating outside the physics. It is a pattern of real interactions in the history. Then one worldline ends and the other continues. The shared history does not vanish, but the braid stops receiving new strands. From a later event, the surviving person can write a letter, say the missing words, or replay the kitchen 1,000 times. Every new signal still travels toward the future. It cannot bend backward into the light cone of the earlier moment. The past event may be real at its coordinates and still be causally unreachable. Grief lives in both facts. The connection was real, and no new exchange can join it. The block universe offers no secret channel back and no promise that the braid continues forever. It says only that the exchanges which occurred are part of the structure. The help was given. The hand was held. The look across the kitchen happened. Physics can describe where those events lie and which signals joined them. It cannot rank their importance. Grief is not a mistaken measurement. It is a response from inside one finite line to the value of a braid that can no longer grow. We began with ordinary pictures. A light pulse crossed a diagonal and forced moving clocks to disagree. One flash drew a cone around everything it could affect. A falling room revealed that gravity is the shape of free motion. A footprint showed why records and memories point toward one side of time. We then asked what those pictures might mean for a whole life. The equations gave us one spacetime containing paths. Limits, records, choices, and finite histories. They did not give us a verdict about what those histories are worth. This series is itself part of the spacetime it describes. So is the writer. So are you. Wherever and whenever these words reach you, the screen emits light. A nervous system receives it. A finite piece of the universe uses diagrams invented by other finite pieces to form a rough picture of the whole. That should make us modest. Every sentence is a local tool. Every diagram is a shadow. We are not standing outside the geometry to inspect it. We are parts of that structure, trying briefly to understand the whole. The book ends by leaving formal argument behind. I know what it is like to enter a room and realize that someone is glad I am there. A half-second of eye contact says, I see you. I know what it is like to hold a hand when the person attached to it is afraid. I know the morning light on a face I love. And the knowledge that my worldline moves away from that exact arrangement while memory softens. These events are not less real because physics can describe their molecules. Physics simply does not contain the language of their value. In the block picture, the moments do not fade, and none receives a second draft. Finally, picture two finite lives. Geometry holds kindness and cruelty with the same indifference. It promises no permanence, fairness, or rescue. It does not notice that either line is frightened or trying or near its end. The structure is indifferent. We are not. Whatever gentleness exists here is enacted locally, when one finite being notices and answers another. That care is not deduced from the geometry. It occurs inside the geometry. And that is enough to make it real. Let the theorem labels and titles recede. Leave the grid faintly present. Leave two histories and one ordinary act of attention.